Well, good evening. We have a special guest tonight to speak with us. Kristina, KD8OXT, is, are you still a PhD student? Not a PhD
yes.
yet? Okay.
Yeah, I'm a PhD student at Case Western Reserve in Cleveland.
Great, great. I heard Kristina speak on, I think it was the ARRL
Eclectic tech, yeah.
Tech. Thank you, thank you. And we got in contact, and in the meantime, she is an author of, co-author of one of a very interesting article in, I think it's the current QST. So it's very, very timely. I really appreciate Kristina taking the time to go through this. And it's something that is really near and dear to all of our hearts, and that is propagation, the science of propagation. We've had several programs on sunspots and 6-meter propagation and general HF propagation. What Kristina will be talking to us about is how we can participate as citizen scientists in furthering our understanding of the ionosphere, for which we all depend. So with that, Kristina, I'll turn it over to you. Thank you.
All right, thanks very much for having me. So the topic tonight is the low-cost personal space weather station, which we call the Grape for reasons which will become clear, and the use of WWV and other time standard stations as scientific utilities to be able to take bottom side ionospheric measurements. I'm going to talk a little bit about the overall mandate of the Personal Space Weather Station, which is an NSF funded project that's being taken on by the HamSCI collective. I'll talk about Grape 1.0, the version of the hardware that is out now that you can buy and build and deploy at your own station. I'll go over the basic theory and some simulations of Doppler shift. We'll look at some plots of data that you might get if you take your own, and how you can extricate scientific meaning from them with some simulations from the FARLAP toolkit using MATLAB and the International Reference Ionosphere. And then I'll talk briefly on pilot experiments such as the Eclipse festivals that we've put together through HamSCI as we're sort of evolving this meta instrument that is being run by members of the amateur community. So the Personal Space Weather Station, this was an idea that has been around in various forms. This particular iteration, I think, has been loosely credited to Ward Silver for suggesting it, but you can see very similar things come up in, for instance, the web SDRs and the Kiwi SDR networks. And so the general idea is just what it says on the tin, that you have a personal weather station, but that it is for space weather, that rather than measuring rain and wind, you are measuring the magnetic field and the virtual ionospheric height and things of that nature in order to gain a deeper understanding of the geospace environment. The ionosphere, which is our particular bit of interest for the Doppler measurement side of things, is a very undersampled system. And we know to some extent the sorts of things that we should see there. Really what we're looking for are essentially weather patterns, and we don't have enough instruments pointing at it to be able to develop an understanding. So it's an exciting time to be playing around with this, because we get to be part of constructing this this large instrument that is interesting from the perspective of a single station, but also interesting from the perspective of many stations together. So this is one of two flavors of Personal Space Weather Station. The Tangerine SDR, which you see the diagram of on the right here, which is being put together by the Tucson Amateur Packet Radio Network. I believe that you'll find it mentioned in an upcoming QST with a rather complete editorial error, so keep an eye out for that. in terms of what the acronym stands for. But nevertheless, the Tucson Amateur Packet Radio Network is taking lead on the Tangerine SDR, which will be a wideband software-defined radio that will be used for a range of experiments. What we're focusing on today is the low-cost personal space weather station, which we've been calling the Grape. And this is a much narrow band version of that mandate. We are looking specifically at time standard stations. We're really only looking at the familiar frequencies of WWV. But as you can see here, there are more than superficial degrees of overlap between these systems. You have a similar architecture with a single board computer. The magnetometer system is meant to be ultimately compatible with both stations, and there's a lot of interplay between how the teams are putting together different parts. So if you join the Tangerine SDR development list, which I also recommend, they usually meet on Monday nights, and they are working on things that have some overlap with the stuff that we do on Thursday mornings. So the Grape, the low-cost personal space weather station, which we call the Grape for a few reasons. The first thing is that it's easier to say than LCPSWS to just say Grape. The other reason is that it's tiny fruit. People like to name electronics after tiny fruit. You've got your Kiwi SDRs, you've got your Lime SDRs, you've got your Raspberry Pis, you know, obviously you've got your Tangerines. And then there's also just the fact that it does its best work in bunches, which by that I mean that the Grape is of most interest when you take data from multiple stations and put that data together and look at it collectively. And then John N8OBJ, who is the lead hardware designer on this, he's runs the electronics laboratory here at CASE. He likes to say that we hope the data will ferment into something quite nice. So this is an image of the Grape station here. Obviously the antenna itself is not pictured, but we have the Raspberry Pi. I assume you can see my cursor. The Raspberry Pi is the main computer. This silver box is a Leo Bodnar GPSDO, retail about $100. And then this little thing with the glowing blue light on the top here is the Grape itself. It is a circuit board that's only about this big. It's a little bigger than a quarter. So that's a Grape station. You hook that up to a wire antenna, and then you can look at the data through your computer. I'm going to skip through these slides a little bit fast with certain highlighted elements. This is the original write-up for what the low-cost receiver is supposed to do. And I like to come back to this, you know, to see what we promised we would get done and to reflect that we've actually done a pretty good job sticking to it. It will be a purpose-built radio receiver. I'll talk a little bit later in the presentation about how you can take these same types of measurements with your ham rig at home. And it's specifically meant to be designed to listen to WWV. So the version 1, which is what's out now, you can build your own. Those ones only have one channel. There will be a version 2 coming out that will have multiple channels to be able to monitor WWV and CHU on different frequencies at the same time. And what we're looking for are frequency shifts that correspond to changes in the virtual height of the ionosphere. We're looking at it as essentially a smooth layer, which for all sorts of reasons is not true, but is an appropriate approximation for what we're doing. Ultimately, there will be 9 channels. Ultimately, the data is recorded at a 1-second cadence. Originally, we were using FL Digi to do a recording a derived data product, and for various reasons, we've moved away from that, and we're doing a more wideband recording, but the data storage is still relatively cheap. And then ultimately, there is a GPSDO at the core of it. These are able to be deployed and intended to be used as small-scale projects for ham radio operators and schools and so forth. Everything's based around a simple wire antenna, GPS disciplined oscillator. Some of this has changed, but the important parts have not, and the Raspberry Pi for the central computing part. Okay, so a word on Doppler shift measurement. We have WWV, with which we are familiar. Between it and your ham station, in this case W8EDU, there is some fixed geographical distance. And we have then the paths that the radio waves from WWV take to get to W8EDU. In the nighttime, when the height of the ionosphere rises up, the path length becomes longer. And in the daytime, when it lowers, the path length becomes shorter. From this, we have a Doppler shift. So we can watch the change in frequency if we look specifically at the frequency of WWV's carrier. And this is the central theory of what the Grape is measuring. There we go. A block diagram. I'll come back to the image from the previous slide in a moment. Here's the circuit board. All of this information is available on the Grape 1 site. And I have a preprint if anybody's curious that does a pretty thorough enumeration of the hardware. But to walk through this diagram together, here's our input power. There's the antenna input and the GPSDO input, which currently we have set up to connect to the Leo Bodnar GPSDO. 5-volt power supply, power indicator light, very useful. Lightning and ESD protection, because we're not heathens. I heard Lloyd talking about lightning protection a bit ago. Selectable input filter, this is just a jumper that you put in to choose whether you're looking at 2.5, 5, or 10 megahertz. Mixer stage, and a differential gain stage at the output. So this is the overall architecture of the board, and you can get it from Osh Park for about $6. As far as the project side of it is concerned, there is one surface mount part. I think everything else is through hole or else comparatively easy. So it's kind of a relatively mid-level kit. So when you're looking at performing these Doppler shift measurements, whether you do it with your Grape off the shelf or whether you do it with your commercial off the shelf ham radio rig, the principle again is that you're looking at essentially this sort of midpoint. And I'm going to make some disclaimers here because, you know, if you spent any time doing DXing, you have a sense that there are things in this model that are hidden. And as they say, all models are wrong, but some are useful. One thing that I'm not including here is multiple hops. Another thing that I'm not including here is reflections off of the E and F layers being separate from one another, or absorption in the D layer, or, you know, multiple propagation modes, things getting spread out. None of that is included in this particular little diagrammatic version of it. But you can get a surprising distance with a relatively simple model here. And the way that I like to imagine these instruments coming together is as sort of a display where we're filling out pixels at the relative midpoints where the single hop propagation is taking place. So if you make these recordings with your home station, you will take FL Digi. If you've ever done the frequency measuring test, which I recommend, you will put it in frequency analysis mode, and it uses an estimation algorithm to seek out the carrier frequency of whatever frequency you tell it to go to. So we're 1 kilohertz below where the carrier is. We're in upper sideband mode. Therefore, we are listening to a 1 kilohertz audio signal. So you hear that tone, and it's not moving around very much, but it will move around over the course of the day. So the tool that was developed for doing the frequency measuring test, where you have some unknown carrier and you're trying to figure that out, you can zero it out according to WWV or whatever you like. That component that it's designed to address that is considered noise when you want to know what the frequency of that carrier is for us our signal. That's the thing that we're looking for. And your result will be ultimately a plot that looks sort of like this. if you use the plotting utility. I don't have anything very eloquent to say about this specific plot. It just happens to be one of the recent ones. Let's see, my little alert that I'm screen sharing is sitting on top of the part where I can see whose plot this is. Node 8. So I think that this is one of David 88Y's here in Cleveland. Here's the sunrise around UTC 12. I'll talk about that in a little bit. The important things to note about these plots, because I'm going to show you several of them. We've got two axes. There's the Doppler shift in Hertz. That's the main one to pay attention to. And that is the black plot, which goes up and down during the day. And then the red in relative dB is the power of the received signal. Each plot covers a 24-hour period, and they're all in UTC. There we go. So as I said previously, it's important to remember that the midpoint isn't the midpoint. So with regard to that particular station, these are simulations using the International Reference Ionosphere. There's no collected data here. This is all physics-based assumptions. And we have on the far left of the plot would be WWV in Fort Collins, near Fort Collins. Over here where you see this faint kind of grainy red line about 2,500 kilometers away is the station here in Cleveland. So this is a two-dimensional slice along the bearing from Colorado to Cleveland. And I've put a line here in red to mark the geographical midpoint between those two spots. So as the day advances, and this is a simulation for June of last year, we're up to 5 UTC. You can see this pink line, and that represents that there is a single hop path that makes it from WWV to Cleveland. I think this is about an hour cadence. These are relatively expensive simulations to run. So there are 3 different frequencies here. The top one is 2.5 megahertz. Then we have 5 megahertz. Then we have 10 megahertz. The color maps don't mean anything except that I was playing with color maps when I recorded them. So as we see these lines appear, what I want you to look at is the apex, the apogee of that, that good path with respect to the geographical midpoint for this station, which is some distance away. And you'll notice that it moves back and forth relative to that geographical midpoint. By contrast, here's a simulation for WA5FRF, which is a station in Texas. And we have his station here much closer and on a predominantly north-south rather than east-west bearing. The different colors indicate which layer of the ionosphere you're bouncing off of. Here in Cleveland, we mostly get those pink F2 paths. And so you can see here that we have reflections occurring, and that they generally happen to occur near the geographic halfway mark. So if I were to take this and put this out to all of the stations that, these are all the stations that reported data for one of our pilot experiments, which was the original Festival of Frequency Measurement. On the occasion of WWV Centennial, we invited ham radio stations to record a day's worth of data with FL Digi over the course of one full 24-hour UTC day. And this was October 1st, 2019. So this particular image I'm showing you is just a simulation. I have actual data a little bit further in the presentation. And this is reported in IEEE Geoscience and Remote Sensing letters. I'll put a link to that in the chat when we finish here. So the thing to point out, though, if each of these is the relative midpoint for the stations that are close, WA5FRF down here in Texas, those midpoints don't move much over the course of the day. For stations that are further away, those midpoints move considerably. And you'll notice also that there's not always at all hours a consistent path. The darker the color of the line, the lower the ionospheric layer that we're seeing propagation off of. So here we are at night, we've got these pink dots that indicate the further propagation paths. So I occasionally come across this image online where someone's posted a picture of the Terminator or the gray line, whichever word you generally prefer. And people have commented on it saying, you know, oh my gosh, how remarkable. What is it like to live there? And of course, you know, I'm going to be living there here in Cleveland in maybe a half an hour or so. But it's easy for us to forget what a significant thing it is for the Earth to be in and out of sunlight with this degree of abruptness. We like to do recordings during eclipses because they let us have a controlled experiment. They let us see darkness over an area of the Earth where we wouldn't normally see it otherwise. But it's easy to forget that the simple fact of going between night and day, which is really almost as significant in effect, happens all the time, and that we can use that as a tool for calibrating our instrument. We can look at the movement of sunrise and sunset back and forth over the course of the year as well. So anyway, when you take your data, what you're likely to see that is a good way to verify that your data is correct is this sunrise peak here. Again, the black is the frequency, the red is the amplitude. So if we look at our little cartoon, the path length decreases when we go from night into day, which means that the received frequency increases. And note that we're looking at a derivative, right? Because Doppler shift doesn't care about the actual length of the path. It doesn't correspond to the length of the path. It corresponds to the change of the length of the path. But anyway, so we will see pretty reliably this jump that is associated with sunrise. And it's not associated with local sunrise. It's associated with sunrise at that midpoint. So here in Ohio, if you were to look at when sunrise is for this peak, it's most significant at the time that the sun rises somewhere near Des Moines, which is our midpoint from here to WWV outside Fort Collins, Colorado. So if we look at the simulation from before, this time I've got the Terminator included, and I've separated out the layer E layer, F1 layer, and F2 layer. Nighttime, we have those F2 paths. The E layer shows up at sunrise during the day. And this also gives you something of a sense of your local ionosphere, right? When you're likely to pick up the signal from WWV with any strength, whether it's during the day or during the night. WA5FRF, the other station who had this reception, we had this conversation once where he was like, oh, well, you know, it's much easier to hear the 5 megahertz signal, the 10 megahertz signal is much more audible during the day. And I was like, well, what are you talking about? You know, because for me, that's not my experience. Because we have different propagation paths, we have different local geospace environments, and we're at different distances from the thing that we're trying to observe. So here we have the 4 plots, and these are 4 days in a row. I wanted to put this in here to showcase some of the variation that you will tend to see day to day. Because when you set up one of these stations, one of the big questions that you have is, okay, I saw it do something. Was that a traveling ionospheric disturbance, or did my dishwasher just turn on? Which thing is it? So being able to figure out the difference between QRN, QRM, something significant happening in geospace, something chewing through your antenna, we have a number of different tools that we can come to. We can look at it over space, we can look at it over time, and we can look for these distinctive features. With these plots, generally these are, let's see, looking for, yeah, 88Y at the top there, so Cleveland Heights, Ohio, got a grid square. We have these recognizable sunrise peaks like the one that I pointed out earlier at multiple points. About 12 UTC generally. And these were taken, yeah, these were taken in June of 2020, these 4. So You'll see a lot of hash during the day. Like I said, we don't have very good reception. You'll notice that the power is very, very low at that time. So a lot of this is just kind of junk because the algorithm that's seeking that that carrier frequency doesn't know where to go because there isn't a strong gradient. So what it'll do in the event that you have two carriers, especially, or if you don't have any particular bin in the frequency domain that is significantly stronger than the others, it'll just run back and forth like a dog between two bones. It has no idea what to do if the frequency is, or if the amplitude is too low. So you got to take that with a grain of salt if the amplitude drops below a certain level. Anything that's on the right side of these plots is probably not that interesting. Now, the upper right-hand one where you see this jump in amplitude and we see this drop was probably something. I don't know exactly what the something was from looking at how the simulations go. There are certain phenomena that will give you that sort of thing when you have a brief moment of connection between a propagation path appearing and then rapidly disappearing. But I can't say for sure just from looking at one plot from one station. So if you were to take these recordings, and all of the plotting utilities to create these are available, this is the kind of thing that you would end up seeing day to day. Now here's an example where we do have some QRM. These were kindly provided by a ham radio operator in Arizona. The two on the bottom are fine. But if you look at the two on the top, let's see, these were 4 consecutive days. We have the last days of May of this year and the first 2 days of June on the bottom. And the two on the top, he had local 10 megahertz noise in his shack that was throwing everything off. So you'll notice that the amplitude is pretty well up there and isn't changing very much. And that correspondingly, the frequency is just kind of flatlined. So that's one way that QRM could manifest if your plot looks something like this. And then the ones on the bottom are much more in line with what we would expect to see from actual geophysical events. So the real trick to this is that the, as we like to say, the grapes do their best work in bunches. You want to have a friend who's near you who also is collecting Doppler data at the same time, and then you compare your data sets. These are two stations. Let's see. These are David 88Y on the left, John N8OBJ on the right. So relatively near grid squares. I want to say these guys are like 8 or 12 miles away from each other. Macedonia, so he's further, but not crazy far, you know. Everything here is 30 minutes away from everything else. This is the same plot, by the way, on the left, if I'm not mistaken, that I showed you earlier, where we have that recognizable sunrise peak. And as we take a look at these, you'll notice, especially during the night when we're seeing signs of these traveling ionospheric disturbances, these waves that travel through the bottom of the ionosphere, there are very, very similar features between these two. So this sort of set of peaks here that I'm circling with the mouse on the left matches up nicely with this set here. And they're not going to be exactly the same. You shouldn't expect them to be exactly the same because it's, you know, you've got buoys at different points on an ocean, but if they get hit by the same wave, then they will register changes that you can identify and match up. So that's the correlation analysis that we're working on. But you can do a lot of this intuitively by examining the different stations that are close enough to each other to have a relatively similar view, but far enough apart that they're not experiencing the same reality. So a bit on looking at data across space and time. On the left here, I have some animations. These are both from 88Y at different times. I think we've got 5 megahertz on the top, 10 megahertz on the bottom. And the 5 megahertz one is relatively good for this. You can see that sunrise peak persisting day to day. So I've taken these plots and I've just, you know, put them together with FFmpeg and made a little animation out of it. And you'll notice the sunrise peak sliding backwards as we're approaching the, oh gosh, I'm gonna get this mixed up. Let's see, this is into April. So as we're coming up to the summer solstice and the time of sunrise is changing over the course of the year, you will see that that peak move. I've got some better plotting utilities now that will take this and automatically put in the sunrise and sunset times, at least locally, to get sort of a first pass bit of information at it. And you can see that effect move along with that line when you put it all together. So that's, you know, over a time distribution at one station. Then these images on the right here, this stacked plot, this is data that was collected from that experiment I mentioned earlier, where we had about 50 stations collecting for the same UT day. The stations that are down here with the white backgrounds, these are all various irregularities in the data collection. So we moved that data out of the data set. Some of them, it was easy to look at it and say, you know, okay, you've got frequency drift. Okay, you've just got one big jump and we're missing a bunch of hours of the day, things like that. But for the ones that are with the gray backgrounds, when lined up by longitude, and we're going east to west, we're going the same direction as the terminator. And then the, I'm not sure what's going on with N9 NVO. This is an old image. The dotted line is sunrise, the solid line is sunset. And you can see that sunrise peak. And when you look at, for instance, you know, these two stations here, where they're very, very similar and they're relatively close to one another, that's the view of the ionosphere from this point. And then when we move over here to, for instance, our Californian stations, we have a different set of waves during the night that they're picking up on. So you can kind of look at these regional views of the geospace environment in this period of time. And this entire experiment was something that we were able to do purely through the generosity of the amateur radio community, using their equipment for this purpose as part of the experimental campaign. The allegory that I always bring into this is the story of the blind men and the elephant, where there's, you know, a number of blind men, and they come across an elephant and they're trying to describe it to one another and sort out exactly what it is. And one of them comes up to the leg and says, okay, this is a trunk-like thing. It's a lot like a tree. An elephant is a tree-like object. Another one comes up to the tail and is like, I don't know what you're talking about. You know, it's more like a fan and it's very bristly. You know, one goes up to the trunk, one goes up to the tusk. The elephant is apparently very forgiving of all of this. And ultimately, they're reporting on different sides of the same thing. So more data needs to be collected if you want to get a complete picture of this very complex object. And here are two of those sets of data from previously. We can see these three stations in the east with very, very strong agreement. They don't even all have GPS disciplined oscillators. These two on the bottom are using their local oscillators at their stations. So you can at least get qualitative data, even if you don't have a GPS DO. But for anything that's quantitative, you really, really want one. And the dark blue is with the noise not taken out. The yellow is after it's been filtered. So 3 stations in the east see one view, 3 stations in the west see another. But within that, within those bunches, they strongly agree. This is a plotting utility that is, I think, 3 days old. This was developed by Bob KD8OXT, who's on the Grape list. And this is a number of different stations. He's only looking at the power here, the black lines in the plots that I've been showing you, for several stations plotted with sunrise and sunset corresponding to one of them. So again, here's that sunrise line, and here's our corresponding sunrise peak. And then there's different things occurring in the night where we can look at these the hash from these different stations and figure out where the features line up. The numbers that he's using to identify these are, let's see, I'm sorry, these are several days. That's what he's doing here, but he's also used them for corresponding stations. This is data from 2 different stations collected at the same time. So several days, one on top of the other, reliable sunrise, very different night to night signals. And then here we have 2 stations collecting at the same time that are some miles away from each other on 10 megahertz. And it makes it much easier when it's plotted this way to see where those points of agreement are. This was one of the early plots that I like to come back to. This was collected during the June 2020 Eclipse Festival. There was someone who approached me early on in the process of recruiting for that. This is one of the pilot experiments that I put together last year. And they offered to translate the instructions for collecting data into Dutch. And the eclipse was in China, so this wasn't necessarily like, a logic. It's not where you would seek to put stations if you were doing everything from scratch, but the more the merrier. And you can have considerable travel from traveling ionospheric disturbances. So I said sure, and they kindly did. And there was quite a bit of interest among the ham community in the Netherlands in joining this experiment. So I got this email from one of the very active hams who's been collecting data not only for that experiment, but also for subsequent eclipse festivals, December of last year, June of this year. And what we have here, yellow is his station, red is a station 5 kilometers away, green is also at that same spot 5 kilometers away on a different radio, and blue is a signal that's not stabilized. So you can see, in a very clear way, the benefit of being able to compare your data to data from a nearby station. And as he said, I don't know what we're seeing, the temperature of the receiver or changing ionosphere, but at least we have fun. So again, Doppler pilot experiments. These are some of the ones that we've held. This was a photo of the eclipse that was collected by one of the volunteers during June 2020. And then some instances of translations and the experiment showing up in the amateur radio news. I will be doing a PR push for the December 2021 eclipse soon. There's going to be a fairly unusual eclipse path across Antarctica. And it'll be very interesting to see the data that we get from incoherent scatter radars and just all the instrumentation that we can put together to look at that. I have in a little bit some photos of a station that I'm hoping to deploy with a Grape in it for that particular event. So one nice thing about the pilot experiments is that the basic questions of putting together a network are essentially answered for you just as a matter of what's available. So when you ask how many volunteer stations can you get, it's whoever volunteers for it, whoever you can convince to volunteer for it. How close they have to be is determined by availability. The kind of data that you need to collect. This is an interesting point. When we need to pivot from one particular method to another, the amateur community is very, very good at making those changes. A problem that I ran into during the June Eclipse Festival, when we were doing this same procedure that we had done for the Festival of Frequency Measurement, we were listening for, time standard stations on 10 megahertz. And if you do this in the United States, you hear WWV. But I had all of these stations in Europe that were trying to listen for maybe WWV, maybe BPM, and they were mostly picking up BPM, but then there was another time station in Italy that doesn't show up on any of the standard lists because they're an experimental station and they're not considered a what's the word I'm looking for? They're not on the BIPM list of time stations. Their signal is just a little bit below 10 megahertz. So as I mentioned earlier, when we're looking, in our waterfall plot, we're looking for that carrier. If we have two carriers, the frequency estimation algorithm will go, And when you look at the plot, you get this fringe. So I would get these very hashed out plots. And you can kind of look at it and say, okay, well, if I look at the top, that sort of looks like a graph. And I look at the bottom, that sort of looks like a graph. So what I did was I asked everybody to record audio. And people did, with about 2 days notice before the event, they recorded audio. And I'm just now getting to the point where some of my students are finally able to process that audio. But we were able to say, okay, we have to make this change and then make it on the fly because of the amateur community members who are willing to put in their time and make those changes. And if you're trying to design a system like this from scratch, you won't get a chance to have that, opportunity to see something that you want to adjust for. But the pilot experiments, because you're taking this pipeline and you're going through the entire thing once, it makes it easier to go back and change out parts and figure out how everything fits together in an early way before you design your ultimate system. Here's the photos I mentioned for the Antarctic deployment. This is a few weeks ago. Things have been cinched down a lot more since then, but we're reusing this box from something previous. We've got our power system will come in here. Grape is right there. And, Raspberry Pi, hard drive. So this will be hopefully, if all goes to plan, an instance of being able to take this and use it as field instrumentation just to see what happens. It's hard to say if it'll actually get deployed for this event because the Antarctic field season for 2021 is very up in the air right now, but it'll be cool if we can pull it off. Another thing that I'd like to get on your radar that would be very interesting, we just had a meeting today with some folks from the Time and Frequency Division at NIST. And I'm managing a scientific working group to look at adding things to WWV's modulation so that we could use that to answer further science questions. So listen in carefully for minute 8 on WWV and minute 44 on WWVH over the next few weeks. And you should hear this collection of chirps and pseudo-random codes and phase coherent tones, which we're using to characterize the transmitters as we're working on figuring out what other projects we could do. And as this process moves forward and with the help of the WWV Amateur Radio Club, I'm really hopeful that we'll be able to put together some interesting citizen science experiments for the community to be able to do that go beyond just looking at the carrier. Hopefully we'll be able to get good time of flight information and build a much more direct understanding of propagation paths through that. There will be a chance for us to look at, path length in a sense that isn't relative in the way that Doppler is. That process is probably going to take a while to add more things to it, but we're getting the testing going, and it's been an absolute privilege and pleasure to work with everybody involved. So ultimately, my goal here is to get folks to join the Grape mailing list. Right now, I should make very clear that the ultimate version of the Grape is not yet out. That will be Grape version 2. It will be the multi-channel version that I walked through all of the specs for at the beginning. What is out now is the Grape version 1, which is the circuit board I showed you, or the schematic. And it's the one that looks like this. Support for this is provided completely by volunteers. The main leads on the project are on the list, but are not generally the ones that are doing development, analyzing data, answering questions, because our efforts are focused on the Grape 2. But what we do have is we do have a very, very active little community that is showing up for Grape 1.0, and that I'm hoping will be able to move to Grape 2.0 when the time comes. As an example of a recent success, what I have on the right here, this was a design for a case for the Grape, an enclosure by Willie N1JBJ. On the left here, we have his printed version of it and the image of the Grape inside. On the right is my printed version, and this being cinched into that Antarctic box. And this was something that he designed, I think, last week and then printed it a couple of days ago. And so everything's coming together in a really good way. So we have information on hamsci.org/grape1. The Google group for the Grape that is linked in the chat is where everything's really happening. So in any event, I highly recommend taking some Doppler measurements with your radio, seeing what you get. The instructions for that are also available in the link in the chat. And it's a really good way to get acquainted with your geospace environment and have that very fundamental ham radio pleasure of listening to WWV. So with that, I will note the NSF grants, the use of FARLAP, and the HPCC here at CASE. W8EDU, HamSCI, and all of the members of the HamSCI collective, the staff at NIST, and everyone who's participated in any of these experiments or worked on support for these systems. So thank you very much. And does anyone have any questions?
Well, thanks a lot, Kristina. Bring me back. Could you give us just as the status collected, as you do the aggregate, as you ferment it, as you age this fine wine, what is
what's the process?
Well, what's the outcome?
What's the outcome? Okay, so the thing that we're ultimately trying to figure out is we're trying to figure out the identification of mid-sized traveling ionospheric disturbances. We're looking for waves in the ionosphere. And, the reasons that we want to figure this out are sort of the same reasons that you want to figure out terrestrial weather, right? You kind of want to know if you're going to have a good propagation day or a lousy propagation day. You're kind of just curious about the system. If you're going to have the equivalent of a 100-year flood like the Carrington event or something like that, it's always good to know more about what the overall climate is like. And all of this feeds into generalized studies of sort of, space climatology. So what we're working on doing here is providing this as a way to supplement existing instrumentation. You have passive instrumentation, you have wideband receivers that are out there, you have active instrumentation like ionosondes, which just send a signal up and it comes back down. But ultimately, there's not that many of them. And being able to put passive receivers everywhere that you go, you can have both higher cadence for your what you're recording, and you can also have much greater spatial density. So essentially anything that you're looking at it with higher resolution. So perhaps you're seeing things that you wouldn't have been able to see before that may be interesting for whatever reasons. And although at the core of it, there's simple curiosity, there is, of course, much interest at looking at the ways in which the ionosphere is coupled into the terrestrial weather environment below in particular, and the space weather environment above. And some of the interesting work in this particular area, Larissa Goncharenko at MIT Haystack has some fascinating papers about using the ionosphere to look at things like what the polar vortex is doing, looking at rapid stratospheric warming events, things that in times of extreme weather, the more advanced notice you can get, the better. If you could know months in advance that there will be a polar vortex that will be quite severe, and you can tell people with enough resolution you should go buy snowplows, that would be obviously a really significant thing. There's not necessarily a direct line from the work we're doing to the ability to have that kind of information, but we are applying a general curiosity about the system through this project. And so generally from the ham perspective, one thing that I hope will also be rewarding, and I think that is of interest for folks that are supporting this type of research, is to have a better ability to estimate what will happen with HF propagation. So I have envisioned the personal space weather station evolving into a box that you keep on your table that gives you a sense of what the maximum usable frequency is to be able to make a contact someplace. Things like that, when you're trying to get that eternal contesting edge are, very desirable. One point that I always try to make about the way that the Doppler measurements specifically are structured, this is an old technique. This means of using the shift of the carrier to make a guess as to the height of the ionosphere dates back to Edward Appleton, and really kind of dates all the way back to Marconi. The fact that Marconi was able to get over the horizon propagation, and Heaviside and Kennelly simultaneously went, it must be bouncing off of something. I bet it's ionized gas. And they came up with this, like within 5 minutes of each other. And then you have the Kennelly Heaviside layer. That's the ionosphere, right? So there's always been this link between particularly what ham radio operators are doing and the edge of what's happening in radio science. And HamSCI is looking to leverage that in a way that is useful both to the scientific community and to the community of amateur radio operators. So what has changed now since Appleton was doing these same sorts of experiments in 1925 is that I have Raspberry Pis and an email and Facebook and the ability to take all of this stuff and put it into a computing cluster and do a lot of analysis all at once. And I can use different techniques of data science and data assimilation and be able to try and extract products from that are things like, hey, it looks like there's a wave and it's going in this direction. What do we think that's related to? So we're still very much in this phase, I think, as a field where we are working on the instrumentation part of it, and we really don't have quick answers yet as to what we might see, but we think it'll be interesting.
Thanks. Other questions for Kristina?
I have one.
Yeah.
Very interesting talk. Can you address the bandwidth requirements for the data? I know that's been an issue before, being kind of excessive for maybe some people. And is that something to do with why you changed your data collection?
Let's see. So for when I do the pilot experiments, there's obviously a big difference between recording, say, an audio signal for several days and doing edge processing to get just the carrier out. There is a concept in geosciences called FAIR data, findable, accessible, interoperable, and reusable. And this is a very strong push. You can find it all over the place in the American Geophysical Union, that when I publish a scientific paper, I should be able to point you back to the most original version of the data that I used that is feasible. Ideally, you should be able to go in and take the information I've given you and repeat my entire analysis if you wanted to. And it should therefore be as easy as possible for you to do so. This is a departure from what we've been doing by necessity for a very long time of taking derived data, in this case, for instance, looking at FL digi and saying, okay, give me just the output of that algorithm. And we're only going to run that algorithm once, and each person's going to run it on their computer, and we'll only have the output. We won't be able to see what happens if we were to run something else. When I take the audio data, as I've been doing lately for the December Eclipse Festival, and analyze it with different frequency estimation algorithms, we can say, okay, well, this one that was meant to look for one carrier found this, but this one that was meant to look for two carriers found this, and we'll try changing these parameters and, you know, and so forth. And we can repeat and extend our analysis for a long time. The downside is the total amount of data that was recorded from that comes out to over a year. So using FLDigi to process all of this in real time doesn't work anymore. And I have some excellent undergrad students who have been working here at CASE for their senior project, and we're working on getting a paper out now on developing an architecture to be able to do all of that processing, because it really is quite a lot on the audio data. Now, ultimately, I think that we'll see something that is sort of splitting the difference between, okay, give me absolutely everything and give me the carrier. We're probably going to have the carrier and then some band around that. The standard that we've been using is the digital RF file standard to record it. I don't have offhand the, you know, general file sizes in mind. But, you know, it's significantly less for the derived product. The usual solution that I have for asking people to get me audio data, if you can't upload it, just mail me a flash drive. And I have probably, you know, 20 flash drives from people over the course of the experiments that I will be mailing back to all of them with QSL cards when I finally get the certificates done. And that's been the easiest way to send it. So yeah, as far as pilot experiments, one nice thing is that you can say, okay, let's collect all of this audio data. For the general system, we will very likely be looking for something that is closer to a derived data product, or at least something where we've thrown away a lot of the information that is not germane to our task. So the goal for it is that you'll be able to archive it locally, automatically upload it. All of this data is ultimately destined for a database, or a file system rather, that will be held at the University of Alabama. That's where it's ultimately going. And Bill Engelke, AB4EJ, is the lead on that project. So that's going to be a little bit down the road. And in the meantime, we've been using a system that's very like Dropbox to just get data from various volunteers. But for current purposes, I think one of the things that's going on is we'll just have people, you know, take their data, look at it and say, hey, here's my finding, you know, genuinely having people analyze what they see from their own systems. Another trend that's worth being aware of in all of this is that for a long time, going back to, you know, SETI at home and early citizen science efforts, there has been a tendency to conflate citizen science with crowdsourced data collection. And by the increasingly stringent standard that is applied for what you call citizen science, what I do in these pilot experiments predominantly of asking people, you know, please take your radio, record data for this period of time, and then send it to me. That is crowdsourced data collection. It does not become citizen science until the volunteers who are assisting in the project have a role in the scientific process, in the forming of hypotheses, in the observation of traits in the data that they collect, in the refining of it. That's when you cross over into something being truly citizen science. And what we really want to encourage, you know, in HamSCI is making sure that we can clear that bar, that for somebody to participate in these experiments or be a member of one of these teams, you're having a full experience of, you know, actual scientific discovery, as opposed to just, you know, collecting data and tying up your rig for 2 days and then never hearing back. And it's tricky from us in the science seats perspective sometimes, because we get all of these data and then we have no time to analyze any of it. But we're getting better at that. We're trying to make sure that the workflow is such that we can draw a direct line from the crowdsourced data and the analysis that we do with the community to, you know, academic publications and papers and things that are referenceable, accessible, all of that sort of thing, and do justice to the community that's doing so much to support our work.
Okay, I guess you do have a solution that if I put one of these online, it's not going to be tying up my internet and I'm not going to be able to use it for anything else.
Yeah, it's a, you know, the just sending a flash drive thing is sort of a quick solution, but it's.
But you don't need it in real time. So
Yeah.
maybe bundle it up and send it at night or something like that when nothing else is going on. That's fine.
Yep.
Okay, thank you.
I've had the NSF buy a lot of stamps before, so.
Other questions?